examples we're going to do today involve those formulas that you have on that sheet that I gave you. Keep that thing handy. Know those formulas. You'll need to know them for the test that we take next week. And you'll need to know them to do things like this. So if we're going to do substitution here, and I'm going to do substitution on this first one, and then the rest of them we'll just use the chain rule on its own. But if I was going to use substitution here, what would I let u equal? The sine of x, right? So then using that formula, we know that dy dx is going to equal, well, e to the u times du dx, right? Do you agree with that? That's just coming straight from that paper that I gave you. So then plugging in what we know, what is e to the u? E to the sine of x. And du dx, I'm going to go ahead and write this off to the side here. Du dx is what? Cosine of x. So we're going to multiply e to the sine of x times cosine of x. That's it. That's all you got to do. It's easy enough, right? This is a typical chain rule problem. If you remember that the derivative of e to the x is e to the x, then the derivative of e to the sine of x is e to the sine of x. We take the derivative and leave the baby inside, and then we multiply by the derivative of the baby, which would be cosine of x. Okay? Any questions about that? All right, then the second one we're going to do is natural log of x squared minus 1. I am not going to use substitution here. I'm just going to use the chain rule right off the bat. Is that okay with you guys? So the derivative of the natural log is what you have on the sheet there is 1 over u, right? And what's u going to equal here? X squared minus 1. So it's going to be 1 over x squared minus 1. But then we have to multiply by 2x. Where'd you get the 2x? The derivative of the baby. So we could write it like this. I actually don't like that. What would be a better way to write it? 2x over x squared minus 1. Pretty easy, isn't it? At least when I'm doing it. Okay, this would be an example of which one? Which formula are we going to use? First, second, third, fourth. That's the second one, right? So in this case, a is going to be 10. So the derivative, I'm going to use y prime here. The derivative of 10 to the x squared is going to be what? Who wants to do this one for me? Did you have a question? Okay.
Are there going to be times where you can only do the chain rule, like you can't do substitution? Can you like choose?
You could always do substitution. If you're going to use a chain rule, you could always do it by doing substitution. Good question. So in this case, we would substitute u equals what? X squared. So let's just kind of do that mentally. We put x squared in for u. We put 10 in where the a is. So what's the derivative going to be? 10 to the x squared, okay, times natural log of 10 times 2x. Cool. You could change this in a few different ways. You could change this using the laws of logarithms a little bit if you wanted to. You could write it as the natural log of 10 to the 2x, or you could even write it as the natural log of 100 to the x power times 10 to the x squared. Are you guys following what I'm saying here? So let's review a logarithm rule here that's going to be useful for us at times. So just looking at this part right here, natural log of 10 times 2x, that's the same thing as 2x times the natural log of 10. And you guys remember the exponent rule with logs? So that's the same thing as the natural log of 10 to the 2x. You remember that? And if you wanted to, then you could evaluate the 10 squared part of it, and it would be 100 to the x power. That kind of simplification, again, like all the other ones that we've done, you would only have to do that if you're trying to match it to a multiple choice response. A lot of times on my tests or on the AP test, they like to make sure that you know that stuff by writing an answer that doesn't look like what you would get right away, but you would have to manipulate it a little bit. So as far as a free response question goes, this right here is a good answer. Okay, any questions about that one? All right. Log base 10 of the tangent of x. So we're going to use that last formula now, right? So the derivative is going to equal. Anyone want to give it a try? Go ahead.
I don't know if this is right. but
Okay.
1 over tangent natural log of 10. Or would it be 10
Tangent of what?
tangent of x,
Okay. Times.
the natural log of 10,
Okay.
and then times, I think it's negative, or is it secant squared for tangent?
Secant squared of x. Yep. What could you do here? Cole?
You can do 1 over cosine squared of x, and then take the secant squared of x, make it 1 over cosine squared of x.
Uh-huh.
Then take the tangent, make it sine x over cosine x, and then cancel out the cosine x.
Okay, yeah. So we could rewrite this as 1 over cosine squared x all over sine of x over cosine of x times the natural log of 10, and then one of the cosine x's is going to cancel, so that's going to go away, that's going to go away. And then probably the best way to rewrite it then would be 1 over the sine of x times the cosine of x times the natural log of 10. Again, this manipulation would be possibly necessary if you're trying to match it up to a multiple choice option. Cool? Exciting?
How long do we get for these tests?
5 or 6 hours. Just kidding. For the AP test or my test?
Figured.
About 110 minutes. 2 55-minute class periods.
Gotcha.
Okay. AP test is roughly 3 hours total. 4 sections. Okay.
Did you take it?
I did.
What'd you do?
Okay. I like this problem because e to the x plus e to the negative x is actually what's called hyperbolic cosine, or at least a version of hyperbolic cosine. You have not been introduced to hyperbolic trigonometry. I actually only have a little bit, and I have a degree in math. It's not very useful in many ways, but it can be. This one's cool because the arch, like the Gateway Arch in St. Louis, that has a hyperbolic cosine shape to it, which is also called a catenary. Anybody ever heard that term? Catenary? It doesn't have anything to do with cataracts, sorry. A catenary is actually the shape that like a rope or a chain would make if you just hold it by 2 points and let it hang. So that little hanging shape is a catenary. So the arch is actually the shape that a chain would make if if you had a chain that was like, what would it be, probably 1,500 feet long. If you had a chain that was 1,500 feet long and you held the ends 630 feet apart, it would make the shape of the arch. This is not the exact equation of the arch, but it's the same type of equation. So let's take the derivative of this one. This is actually a fairly easy one, or at least it can be a fairly easy one. We want to go term by term here. What do you think, Cole?
Well, the first one, it would just be e to the x times 1, right?
Yep, e to the x times the derivative of that, so it would be e to the x times 1. And how about the second one?
Negative e to the x.
Yeah, negative e to the
Negative.
negative x. All right, so I'm going to take the negative part off here just for a second. This is the derivative of the mother keeping the baby inside, right? And then we multiply by the derivative of the baby, which is that. So it's just going to be e to the x minus e to the negative x. It's actually the conjugate of, the derivative of that function is the conjugate of itself. You guys remember what a conjugate is, right? Yes?
Okay, I didn't really understand that at all.
Didn't understand it all. Okay, that's fine. So basically what we're doing here is we're letting that equal u. So u equals negative x. So that means that du dx is going to equal negative 1. So then the derivative of this is going to be e to the u du dx. That make sense?
Yeah, it's just really confusing.
It's okay. So then that would, replacing the u's with x's, then it would be e to the negative x times negative 1, which would be negative e to the negative x.
What happened to the first one?
This,
The X.
this,
Yeah.
the derivative of e to the x is e to the x.
Okay.
So we took the derivative of this and got that. We took the derivative of a positive e to the negative x and got negative e to the negative x.
Okay.
Does that make sense? Okay. Okay, here's where it gets really tricky. And we have to use, we could use inverse functions here to help us out. We will definitely have to use implicit differentiation here. I will tell you that none of the formulas you have written down right now will help us with this function as it's written. The problem is, and the one that looks like it might be useful is the one that tells us how to take the derivative of a to the u. The problem is, in that formula, the a has to be a constant. It can't be a variable. So if you have a variable as a base and a variable in the exponent, then you're going to have to do something else. And we're going to do something called logarithmic differentiation. So, first of all, does anybody see any logarithms in this equation? No, me neither. Do you see them? Okay. So what we're going to do is we're going to introduce logarithms. Now, we can introduce a logarithm of any base that we want. Which base do you think would be easiest to work with? E. Natural logs, in calculus, natural logs are a lot easier to work with than the other ones. And if you look at the derivative of the natural log of u and the derivative of the log of any other base, which one's simpler? The natural log, right? So what we're going to do is we're going to take the natural log of both sides. We're going to take the natural log of y and set that equal to the natural log of x to the x. Now, what did that do for us? Cole?
Now we can use the things on the sheet.
Not quite yet.
Bring the x out in front of the natural log.
Yes, this x here we can take out front, and we can write it as x times the natural log of x. So the natural log rules, the natural log properties, are going to allow us to manipulate problems like this into something that's easier to take the derivative of. So what we have now is the natural log of y equals x times the natural log of x. And now what? What do we do next? Get what to one side? Okay.
You can use this formula to do the left side.
Okay, yeah, we can use that formula to do the left side. So what we can do now is we can take the derivative of both sides. Since we don't have y by itself, what kind of differentiation are we going to have to use? Starts with an I. Implicit. So we're going to do implicit differentiation and take the derivative of each individual piece by itself, or each individual term by itself. So what is the derivative of the natural log of y? It's going to be 1 over y times dy dx. Yeah, we could throw 1 in there also if you wanted. But since we're taking the derivative of y with respect to x, we have to multiply by dy dx. That's the key to implicit differentiation, right? And that's going to equal the derivative of this side. And what are we going to have to use on this side? Product rule. Yeah. Derivative of the first. 1 times the second. Natural log of x. Plus the first. Times the derivative of the second.
1 over x
Ooh, I like what's going to happen there.
times dx dx.
Yep, times dx dx, which is 1, right? Okay, let me clean this up here a little bit. Now what?
X and 1 over x fall out.
Okay, the x and the 1 over x, those are going to cancel each other out, and this term is going to become a 1. So what we have on the right side is the natural log of x plus 1. What are we trying to solve for here? We're trying to figure out what dy dx is, right? So dy dx is going to be y times the natural log of x plus 1. You agree with that? Is that okay like that? No, it's not. What's wrong with that? Was this relation here defined implicitly when we started? No. So would it be appropriate to leave an implicitly defined derivative when we finish? No. In other words, since there were no y's here, we don't want any y's here. So how do we get rid of the y? Cole? Huh? Okay. Vimmel?
Can you plug in x to the x?
Yeah. We know that y is equal to x. That was given to us. And so we just rewrite it like that. It's kind of fun, isn't it? I like the problems that make you think a little bit. That's just a personal thing, though. All right, so can anybody explain to me why we're going to have to do this last problem? Can anybody explain to me why we'll have to do something similar on this one? What did you say, Ethan? It has an x in the exponent and in the base, right? So we have the variable in the base and the exponent, so we're going to have to use logarithmic differentiation again. Do you guys want to give it a try on your own and then do it together?
Sure.
What are we going to do first?
Natural log.
Take the natural log of both sides. And then what? Move the exponent down, so we're going to have the natural log of y equals sine of x times the natural log of x. Okay, then what? Differentiate with respect to x, so we have 1 over y, but we're taking the derivative with respect to x, so dy dx equals product rule, right?
Yes.
Okay, what's the derivative of the first? Cosine of x times the second plus the first times the derivative of the second 1 over x times dx dx, yeah, or times the derivative of x with respect to x. Okay, now what? Multiply by y. Are you guys okay if I multiply by y and substitute x to the sine of x in for y at the same time? Yep. Maybe? Okay, so we're going to multiply both sides by y, but y is x to the sine of x times the quantity cosine of x, natural log of x, plus sine of x over x. Or you could do 1 over x times the sine of x, either way. This is just a little bit of a simpler way to write it. Any questions about that?
That's the answer.
That's the answer.
Oh my gosh, that's actually.
Yay.
This is what happens.
Oh, come on, it happens all the time.
No, not often.
All right.